Okay, stats. Chapter 10 is all about hypothesis testing. It's when you're actually going to run an experiment and draw some conclusions. So the primary goal of 10.1 is to talk about the language and how you do or don't do what you do or don't say during an experiment, for example. So hypothesis testing is a procedure based on sample evidence and probability used to test a statement regarding a characteristic of one or more populations. First thing you have to do is make a statement. Then you have to collect evidence, and then you analyze the data to assess the accuracy of your statement. And first thing always you have to test is the null hypothesis. It's denoted H0. It's a statement to be tested. It is a statement of no change, no effect, or no difference. It's like the baseline assumed to be true statement that maybe you're trying to prove is something else might be true, or at least reject the truth of this. So the null hypothesis is the status quo. Unless you have evidence of the contrary, you assume it's true. We're either going to find evidence that supports the statement in an alternative hypothesis, or it will not support the statement. Now, an alternative hypothesis is a statement that we're trying to find evidence to support that's generally different than the null hypothesis. There are about 3 different ways this can happen. Equal versus not equal. So that's where you say the parameter is some value. For example, I said the number of people who prefer dogs to cats is 0.7 or 70%. Then you would test, well, I think the number is different. Could be higher, could be lower. I just know the number is not 70%. Equal or less than. If I were to say, I think the number of the null hypothesis of the number of people who prefer dogs to cats was 70%. I said, no way, it's less than that. I'm putting all my eggs in the less than basket, so I'm saying I think that number is less than. In fact, I'm not going to test anything above it, only testing to the left. And then there's the opposite, where I think the number is greater, and I'm only testing things above him. So we can either have a two-tailed test where you're saying it's just not equal to, a left-tailed where you think it's less than, or a right-tailed where you think is greater. Positive and negatives. For the two-tailed test, if it's a really strange outlier on either side, it still counts. For a left-tailed test, since you're putting all your eggs in that one basket, then you have more room to find outliers. And if it's a right-tailed test, you put all your eggs in the other basket. So that creates all of your extra outlier space on that other side. Okay, so let's just practice making our hypotheses. We're not going to do any tests in this chapter. We're just going to talk about some conclusions and how to write our hypotheses. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So the word is different today. It didn't say greater than or less than, means it's a two-tailed test. So we're checking both sides. So the null hypothesis is the old experiment. So that would be the probability that they volunteered. 62% is 0.62, and we use p because it's a proportion. Now he's testing whether or not it's not equal to that anymore. It could be above or below. He just thinks it's different today. And number 2, according to a study published in March 2006, the mean length of a cellular phone call was 3.25 minutes. A researcher believes that this has increased since then. Okay, so mu, the mean length, was 3.25 originally. He thinks it's increased, which means here we've got 3.25. He thinks it's all on the right side, so it's a right-tailed test because he wants it to increase. So his alternative hypothesis is mu is now greater than 3.25. And lastly, according to the CDC, 15.2% of American adults experience migraines. Stress is a major contributing factor. A massage therapist feels she has a technique that can reduce the frequency and intensity of migraines. So her argument is normal population, H0 is 0.152. She thinks she can reduce it, so for the people receiving her treatment, she thinks she can make it less than 0.152 because it's a left-tailed test. So these are the types of setups you can have. And again, it's the proportion, so we use P. Now, naturally, if we could find evidence that supports or doesn't support our alternative hypothesis, but what we always do is we either reject the null hypothesis or we don't reject it. Now, there's some outcomes here. We could reject it when the alternative hypothesis is true, which means we did the right thing. We could not reject the null hypothesis because the null hypothesis is true. But there's always a chance we can make an error. What happens if we reject the null hypothesis, but the null hypothesis is actually true? It's called a type 1 error. And what if we don't find the evidence to reject the null hypothesis when in fact we should have, because the alternative hypothesis was true? That's a type 2 error. Now, this little chart is just to help guide you. Rejecting H0 when H0 is false is the correct decision. Similarly, not rejecting H0 when H0 was true is also correct. But if we reject H0 but H0 was true, this is type 1. This is type 2, when we don't reject it but it's false. It's kind of like a criminal trial, guilty, not guilty. If the defendant is guilty and the court finds him guilty, that's correct. If the defendant is innocent and they find him not guilty, also correct. But if you get a guilty verdict when the defendant is innocent, that is an error, but it's a type 1 error. Similarly, if you don't get a guilty verdict but the defendant is guilty, that's type 2. Most people tend to think there are times when you really want to avoid type 1. This criminal thing is a perfect example why I think it's arguably better to leave someone guilty out than to put someone who's not guilty away. Maybe you disagree, but I think better to be on the safe side. Okay, as a reminder, we either reject the null hypothesis or we don't. We never accept the null hypothesis. We don't have the whole population. If they're talking about type 1 error or type 2 errors, we call the probability of a type 1 error alpha, the probability of type 2 error beta. Most of the time, when they tell you the level of significance, that is the alpha, the probability of type 1 error. It's usually chosen by a researcher before things are collected. As the probability of type 1 error increases, the probability of type 2 error decreases, and vice versa. So your error is kind of split between them, and you kind of control what error has what power. So for each of the following claims, explains what it be to make a type 1 or type 2 error. So in 2008, 62% of American adults regularly volunteered. A researcher believes the percentage is different today. So type 1 is where we reject the null hypothesis even though it's true. So you conclude it is different when it actually isn't, when it's still 0.62. Whereas a type 2 error is where you say it's still 0.62, but, so you say, or you conclude it's still 0.62, but it actually is different today. So that's the difference between these two types of error. One is you're drawing a conclusion. Each one you're drawing a conclusion is that's wrong, but one of them is you assume it's different when it's not, versus you assume it's not different when it is. Similarly, according to a study published in March 2006, this is the phone call one. A researcher believes the calls increased since then. Type 1 means you rejected the 3.25 minute average, so you conclude the mean length is longer. It's greater than, or longer, this is shorthand, when it isn't. And type 2, you conclude it's still 3.25. You can't reject the 3.25, but in reality, it has increased. And we'll talk more and finish 10.1 in the next video and move on to 10.2.